Okay, so this video is all about the Poisson distribution. Okay, and so Poisson is my second of my discrete distributions. Now remember, discrete means counted. So this is something that is going to be counted. So it's the number of cars that go past, the number of earthquakes that happen, the number of weeds per square meter. So, you know, you're beginning to get an idea that there's definite numbers, they're counted. But this is a little bit different from the binomial, which is my other discrete distribution. Unlike the binomial, where you're told a probability of success and you're told the number of times that will happen. In the Poisson, we've got this interval of area, of space, of potentially time, which I'm interested in working alongside. And that's something that's measured. So you've got to keep your wits about you with the Poisson, okay? It's a discrete distribution that's in an interval of time or space or area. So again, a bit like the Poisson, by the binomial, we have four conditions that we have to satisfy. And the best acronym that I've come up with so far, or I've heard of so far, is RIPS. Okay? So, in a binomial or in a Poisson, my events have to occur at random. So, I've got an interval of time or area or whatever. So, if I go back to my weed analogy, if I go out into my garden and look at the lawn, the amount of weeds per square meter of lawn is random. That they're either there or they're not. Each instance of my Poisson distribution has to be independent. If I go out into the garden and again look at the weeds, I have quite a lot of weeds in my lawn at the moment. I will notice that just because there's a weed nearby didn't stop another weed growing. Okay, so each weed is fighting for themselves. Okay, and then we get to the last two. Now, P stands for proportional. Now, what I mean by that is the following. If I go and look at the number of weeds that are per square meter in my lawn, the amount of weeds on average will be proportional to the size of the block that I'm looking at. So if instead I'm looking at a square meter, I look at a square 10 centimeter block, then there are 100 10 centimeter blocks in a square meter. So the average number of weeds in a 10 centimeter block should be 100th of the square meter block. I normally use the other analogy when I'm talking about proportionality, that if I insult one person every 10 minutes in one of my lessons, then in an hour-long lesson, I should insult them on average 6 times, because it's proportional to the size of the interval. Okay? So that's my third condition. And my fourth condition is the one I'm least happy with. EOUS is I cannot have more than one event happening at once. So if I go back to my earthquake analogy just for a second. I can't have two earthquakes at the same time. They cannot happen simultaneously. So those are my conditions. I accept that the last one's a little bit dubious, particularly having the not in brackets. Okay. But those are my different things. So if I look at my thing, it says we've collected data about assisting councils and water suppliers to produce water effective methods. Prior to the study, it's estimated each person using flushes the toilet on average 4.7 times per 24-hour period. So, in 48 hours, on average, you'd expect people to flush that 9.4 times. The number of times flushing is proportional to the interval. So I'm meeting my requirement for proportionality. I would kind of hope that toilet flushes are random. I hope no one's got a bathroom schedule like Sheldon from The Big Bang Theory. And you certainly can't flush a toilet simultaneously because you might only have one toilet. And that's just getting a bit weird. Okay? The only one that I'm beginning to look at this and kind of go, independence. Each toilet flush is independent. Maybe, maybe not. And that's a debatable one. And that's one why I'm not going to come up with one side or the other. If I was doing this question and I was giving a reason why I might not like this distribution, I might choose to look at independence as a possibility because having gone to the toilet once, you probably won't need to go to the toilet again in the same interval of time for a while. Our interval of time is 24 hours, so that's quite a long window. So you should probably sort that self out, but depends on how much you're drinking and all sorts of other factors. So I'm going to leave that one for a minute, but you get the idea about a Poisson distribution. So the key things is a Poisson is discrete. You've got 4 conditions for it. Again, like the binomial, you may be a little bit hazy about one of those conditions, but you probably will be okay because you can justify the others enough and that one just while you get through that part of the question and then come back to it later. And the next video is going to be about us working out that probability. Use the probability distribution model to estimate the probability of a person flush the toilet less than 5 times in 24-hour period. Before we finish this video, I do want to answer the second part of this question, much same as I did in the first one. So what they're asking me to do is give one reason why it may not be appropriate to use the Poisson distribution to model the number of toilet flushes for any 4-hour period. Right. When I come to scale it up and down, we have to treat each interval as the same as the giant interval, just scaled up or down. And this is where we get a bit of a problem with this situation, because toilet flushing happens more during your waking hours than it does during your sleeping hours. Your body is designed not to have to wake you up to go to the toilet as best it can. So therefore, depending on which 4-hour period you're talking about, if you're talking about from midnight to 4 a.m., I would expect that to be lower than the time from 8 a.m. to 10 a.m. It also changes, it depends on whether you're at home or at school during the day, because it doesn't tell you where you are. So, if you are at home during the day, you may drink more water than if you're at a school day, or vice versa. You may drink more at school. Who knows? So there's so many problems with the independence and with the proportionality if you scale the time down to 4 hours, that I don't think a Poisson distribution would be appropriate. Okay, you're always going to get going to the bathroom as random, and you're always likely to get you're not going to be able to go simultaneously. Although if you have multiple bathrooms in your house, maybe that is a case, and that's a problem at that point. Okay, so go through the things in context and then come up with a reason why it may not work in this case. Okay, so that's this video. Next video, we're going to be working out the probability for a Poisson, and then we will talk inverse.